So I want you to just take a second and picture something for a minute. Put yourself right in the boots of a soldier standing outside in this completely dark, austere environment.
Right, like a forward operating area or something.
Exactly, like a total blackout zone. It's the middle of the night, clear skies, and it is freezing cold. You look up at the stars and, if you really have the patience to just stare, you will eventually see this tiny, steady point of light just sliding across the blackness.
Yeah, and it doesn't blink at all, not like a commercial aircraft.
Right. It just glides. It looks, honestly, incredibly serene. So perfectly precise. But the reality is that the quiet precision you're watching is a complete illusion.
Oh, absolutely. It's totally chaotic.
Yeah. What you are actually looking at is a continuous mathematical battle between the sheer violent force of velocity and the invisible crushing grip of gravity.
Which is a phenomenal way to think about it, honestly, because that point of light is literally in a state of constant free fall.
Like it's just falling out of the sky.
Right, it's plummeting toward the ground. But it is moving forward at such an extreme speed that the Earth is physically curving away beneath it before it can ever crash.
That is just wild to think about.
It is. What looks like this peaceful glide through the night sky is actually an incredibly violent physical reality, and it's playing out hundreds or thousands of miles right above your head.
And understanding the mechanics of that violent reality is exactly what we are doing today. Welcome to the Doctrine Deep Dive.
Glad to be here, as always.
So we are pulling a hefty stack of military space doctrine off the shelf today. Specifically, we are diving into Chapter 4 of the United States Army Space Reference Text, which is titled Satellite Orbits.
And we're also bringing in some supplementary learning materials, right? Covering Kepler's laws, Newton's laws, gravity, and orbit types.
Yes, exactly. We've got a lot to cover. But we are not just going to sit here and read a syllabus to you.
No, definitely not. That would be brutal.
Right. We are dragging this material entirely out of the classroom. Because for you, the listener, mastering this really isn't just some academic exercise.
No, it's foundational. If you are going to be a planner or an operator in any modern military context, you have to understand this domain.
You absolutely do, because you just cannot effectively plan modern joint all-domain operations without knowing how these orbital mechanics actually work.
The space domain completely dictates the timing, the reach, and, well, the absolute limitations of almost everything we do on the ground.
Yeah, and at sea and in the air.
Exactly. We rely on it heavily for navigation, for communication, and intelligence. But space is not magic. It is strictly governed by physics.
Right. And to help us translate all these really heavy physics concepts into tactical operational reality, I am joined today by our resident master's level professor and military strategy expert in space operations.
Always a pleasure to help break this stuff down.
So, our mission today for this deep dive is to master the foundational physics, build out the mathematical language we use to find these assets, categorize the specific neighborhoods in space, and then finally unpack the messy, real-world perturbations that constantly try to pull our satellites out of the sky.
I am genuinely thrilled to get into this, because before a commander can even think about requesting a communication satellite link, or, asking for an intelligence sensor to scan a specific valley, planners first have to submit to the invisible rules of space.
You just can't negotiate with physics.
You really can't. You have to understand the fundamental forces that dictate exactly how objects move in a vacuum, because those forces dictate what your assets can and absolutely cannot do.
So let's just start right there with those invisible rules. If we're talking about the fundamentals of orbital mechanics, we actually have to rewind the clock quite a bit, right?
Yeah, quite a few hundred years, actually.
Right. We cannot even begin to talk about modern military satellites without talking about a guy sitting under an apple tree in the 1600s, Sir Isaac Newton.
He really is the foundation of everything we do in space operations. Back in the late 17th century, Newton formulated 3 laws of motion, along with the law of universal gravitation.
And he was doing all this with just quills and parchment.
Exactly. And even though he was working with such basic tools, those 4 concepts completely define how a multi-billion-dollar military satellite behaves today.
It's kind of crazy to think about.
It is. Let's look at Newton's first law, which is the law of inertia. It essentially states that a body at rest will remain at rest, and a body in motion will remain in motion in a straight line at a constant speed unless it's acted upon by an external force.
I always try to visualize this one because it is just so counterintuitive to how we actually live down here on Earth.
Oh, absolutely. Earth is full of friction.
Right. On Earth, if I push my coffee mug across the table, it stops. Friction literally stops it. But in space, if I am on a spacewalk and I throw a wrench as hard as I can, that wrench just keeps going forever.
It doesn't slow down, it doesn't drop, it just travels in a perfectly straight line right into the void. That is inertia in its purest form.
Because there's no air to slow it down.
Right. In the vacuum of space, you do not have the atmospheric friction that robs an object of its kinetic energy. So that wrench will travel at the exact same speed, in the exact same direction, until it either hits something or enters the gravitational pull of another body.
Okay, but satellites do not travel in straight lines. They travel in curves, right? Orbits.
Exactly. So if we apply Newton's first law, the fact that the satellite is curving tells us there must be some massive external force constantly acting on it to bend its path.
Because otherwise it would just shoot straight off into deep space.
Right. If that mysterious force magically turned off, the satellite's inertia would immediately cause it to fly off in a straight line forever.
Okay, we will get to that specific bending force in a second, but I want to stay on the behavior of the object itself for a minute. Let's look at Newton's second law.
Ah, the relationship between force, mass, and acceleration.
Yeah, the text describes it that way, but how does that actually translate to an operator who is just sitting at a console trying to manage a space asset?
Well, it translates entirely to momentum, which ultimately translates directly to fuel.
Okay, unpack that a bit.
The second law states that the acceleration of an object is directly proportional to the force applied to it and inversely proportional to its mass. So think about it practically.
Okay.
A modern military communications satellite is not some tiny little lightweight box. It can literally be the size of a school bus and weigh several tons.
And it's moving incredibly fast.
Roughly 17,500 miles per hour. That is an astonishing amount of momentum.
So if a theater commander suddenly says, hey, I need that satellite move to cover totally new area of operations by tomorrow, they're basically asking to change the momentum of a school bus traveling at hypersonic speeds in a frictionless vacuum.
Exactly. That is exactly what they're asking. And to change that momentum, to accelerate or decelerate or change direction, you have to apply a massive amount of force.
And you generate force in space by burning fuel.
Yes. And fuel is the single most precious, finite resource in the space domain. Once a satellite runs out of station-keeping fuel, it is completely dead.
It just becomes a multi-billion-dollar piece of space junk.
It does. So Newton's second law is this constant, really harsh reminder to military planners that maneuverability in space is incredibly expensive and highly limited. You just cannot fly a satellite like a fighter jet.
Which leads right into the mechanics of how we actually generate that force in the first place. Newton's third law.
Right. For every action, there is a reaction, equal in magnitude, but opposite in direction.
And this is the fundamental principle behind rocket engines and satellite thrusters, isn't it?
It is the only way we can physically move in a vacuum. Down on Earth, a car moves forward because the tires push against the road.
And an airplane moves because the engines push against the air.
Exactly. But in the vacuum of space, there is no road and there is absolutely no air. There is literally nothing to push against. So if a satellite needs to move forward, it has to physically throw its own mass backward.
It's throwing mass. You mean like the chemical propellant?
Yes, exactly. The thruster ignites, the chemical propellant expands into this highly pressurized gas, and that gas is expelled out the back of the nozzle at an extreme velocity.
So the gas escaping backwards is the action.
Right. And that violent action creates an equal and opposite reaction that pushes the heavy satellite forward. But again, you only have so much mass, so much propellant on board.
Every single time you invoke Newton's third law to adjust your orbit, you are literally throwing a piece of your satellite's lifespan right out the exhaust pipe.
That's a great way to put it. You are burning your lifespan.
Okay, so building the picture here. We have inertia trying to carry the satellite away into deep space in a straight line. We have momentum dictating how brutally hard it is to change its speed or direction. And we have action-reaction giving us a very limited way to maneuver using finite fuel.
You've got it.
But earlier you said inertia dictates that the satellite wants to fly straight and something is bending it. What is the invisible external force constantly bending that straight line into a continuous circle around the planet?
That brings us to Newton's law of universal gravitation. Gravity is the invisible tether.
Gravity is what's holding it all together.
Exactly. Newton realized that every single object in the universe attracts every other object with a force that is directly proportional to the product of their masses.
So the Earth is massive, meaning it exerts A massive gravitational pull.
Right. It exerts a huge pull on the satellite, constantly yanking it downward, pulling it away from its straight inertial path.
Wait, if everything attracts everything, does that mean the tiny satellite is actually exerting a gravitational pull on the Earth, too?
Well, mathematically, yes. The satellite is pulling the Earth upward just as the Earth is pulling the satellite downward.
Really? I never thought about it like that.
Yeah, but because the Earth's mass is just so incomprehensibly huge compared to the satellite, the Earth's movement is virtually zero. Meanwhile, the satellite is the one that gets swung around in a huge circle.
That makes sense.
But there is a crucial caveat to the gravity equation that military planners really have to understand. The force of gravity is not constant everywhere.
It decreases with the distance, right?
Yes, it decreases with the square of the distance between the two objects.
Meaning the further away you get from the Earth, the weaker that invisible tether gets, and it gets weaker very quickly.
Very quickly. And this is why altitude is absolute destiny in space operations.
How so?
Well, if you put a satellite in a very low orbit, it is feeling the full violent force of Earth's gravity. To avoid being pulled straight down into the atmosphere and burning up, that satellite has to travel incredibly fast to maintain its orbit.
But if you go further out,
if you launch a satellite much further out into deep space, the gravitational pull from the Earth is dramatically weaker. Therefore, the satellite just doesn't need to travel nearly as fast to fight off gravity.
So this is why low-altitude satellites whip around the Earth in 90 minutes, while high-altitude satellites take an entire day to complete one lap.
Precisely. It is all about how hard gravity is pulling them based on their distance.
I want to make sure I am really visualizing this tug-of-war between velocity and gravity correctly. I was thinking about this baseball analogy.
Oh, the baseball analogy is great for this. Walk me through it.
Okay, so if I just stand in a field and throw a baseball as hard as I can, gravity immediately starts pulling it down. It goes a little way, follows a curve, and hits the grass.
Right. Gravity wins.
If I have a major league pitcher throw it, it goes way further before it hits the ground, but gravity still pulls it down eventually.
Right.
But the Earth is a sphere. It is round. So if I could somehow throw that baseball incredibly fast, say roughly 5 miles per second, gravity is still pulling it down at the exact same rate, right?
Yes, the downward acceleration is the same.
But because the baseball is moving forward so fast, the actual surface of the Earth is curving away from the ball at the exact same rate the ball is falling.
Yeah.
So it falls, but the ground drops away. It falls, the ground drops away. That's essentially what an orbit is.
Yes. It is a perpetual state of missing the ground.
Just constantly falling, but missing.
It's a phenomenal way to describe it. If you throw that baseball at roughly 5 miles per second, or, to use the precise math from our reference text, 5.59 kilometers per second at an altitude of 1 Earth radius, that ball achieves what we call circular velocity.
Circular velocity, got it.
Its forward momentum perfectly matches the downward acceleration of gravity and the curvature of the Earth, so it will fall forever in a perfect circle without ever hitting the dirt.
Okay, but wait. What if I just absolutely launch that baseball? I increase the velocity well past 5 miles per second. Doesn't it just break the tether and fly away from Earth entirely?
Well, not immediately. This is where it gets really mathematically interesting. If you increase the velocity past circular velocity, the orbit doesn't just break, it actually stretches.
It stretches out.
Yeah. The momentum pushes the ball further out into space, overcoming the gravity temporarily, so the path becomes an ellipse, a stretched out oval.
Oh, I see.
The ball travels far out, but gravity is relentless. It eventually slows the ball down, halts its outward expansion, and just pulls it right back around.
So it is essentially on a bungee cord. It stretches way out, slows down, and then snaps back toward the Earth.
Exactly. But you are right that there is an ultimate breaking point. If you throw that ball fast enough, specifically around 7.91 kilometers per second at that same altitude, you achieve what is called escape velocity.
Escape velocity. That's when the bungee cord snaps.
Right. At that specific speed, the kinetic energy of the object is so massive that the Earth's gravitational pull can never slow it down enough to pull it back.
So it just leaves.
Yes. The trajectory ceases to be a closed loop. It becomes an open curve, geometrically a parabola or hyperbola, and that object leaves Earth's sphere of influence forever, just heading straight out into the solar system.
Wow, so Newton really gives us the why. He gives us the brute force physics of inertia, momentum, and the invisible tether of gravity.
He laid the entire foundation.
But there was another scientist who explained the how. Like how these forces actually dictate the precise geometric shapes of the orbits.
Mm-hmm.
And what really blows my mind is that he figured this out decades before Newton even wrote his laws.
You're talking about Johannes Kepler.
Yes, Johannes Kepler.
He is such a fascinating figure. He was a mathematician working in the early 1600s. And keep in mind, this is long before the invention of the rocket, before computers, and largely before the telescope was even a reliable scientific instrument.
He had none of that technology.
None of it. What he had were massive books full of astronomical observations, meticulously recorded by another astronomer named Tycho Brahe.
Just pages of numbers.
Just endless columns of numbers. Kepler spent years just staring at these numbers, tracking the movement of the planets, and he formulated 3 laws of planetary motion.
Which is incredible.
And here is the truly brilliant part. Those exact same laws that dictate how Mars orbits the Sun apply identically to how a military reconnaissance satellite orbits the Earth today.
That is just wild to me. Let's walk through his 3 laws. Kepler's first law is the law of ellipses.
Right.
The text says it states that the orbits of planets, or in our case, artificial satellites, are ellipses, with the center of the Earth at one focus.
Right, because before Kepler, everyone just assumed that orbits had to be perfect circles because circles were considered geometrically perfect.
Right, the perfect celestial spheres.
Exactly. But Kepler's math proved them all wrong. He realized that orbits are ellipses, which are essentially slightly squashed or stretched out circles. But the really critical part of his first law is the concept of the focus.
Yeah, I wanted to ask about that. A focus isn't just the dead center of the oval, right?
No, it is not. If you want to draw a perfect circle, you put a pin in the center of a piece of paper, attach a string, and draw around it. A circle has one center point.
Right, easy enough.
But an ellipse has 2 anchor points, which are called foci. To draw an ellipse, you would put 2 pins in the paper, loop a string around both of them, and draw.
Okay, I can picture that.
Kepler proved that the Earth does not sit in the exact mathematical center of the satellite's orbit. It actually sits off to the side at one of those 2 focal points.
So if the Earth is offset to one side of this oval, that means the distance between the satellite and the Earth is constantly changing as the satellite flies along its path.
Exactly. Sometimes it's closer, sometimes it's farther. And that changing distance is the entire foundation for Kepler's second law, which is the law of areas.
Okay, the text defines the law of areas by saying a line joining the satellite to the Earth sweeps out equal areas in equal times.
You know, it's a bit dense.
I have to be honest, when I read that, it just sounded like total academic word salad.
Yeah.
What does sweeping equal areas actually mean for a satellite operator?
It sounds like word salad, but it's actually describing something incredibly dynamic. Because the Earth is offset at one focus of the ellipse, there is a specific point in the orbit where the satellite is closest to the Earth.
Okay, the closest point.
That point is called the perigee. Conversely, there is a point on the exact opposite side of the orbit where the satellite is furthest away from the Earth. That point is called the apogee.
Okay, so perigee is close, apogee is far. Got it.
Now, Kepler's math says that if you draw an imaginary line from the center of the Earth to the satellite, that line has to sweep across the exact same amount of square mileage inside the ellipse over a given time period, say 1 hour.
Sweeping out square mileage.
Oh.
Okay.
When the satellite is at perigee, close to the Earth, that imaginary line is very short. So in order to sweep out a massive area in that hour, the satellite has to move incredibly fast along its path.
I see.
When the satellite is way out at apogee, the line is very long. It doesn't need to move very far along its path to sweep out the exact same area. Therefore, the satellite moves much slower.
So the speed of a satellite is not constant at all. It is literally constantly accelerating and decelerating.
Precisely. It whips around the Earth at blinding speed at perigee, and then it coasts and slows down as it climbs all the way up to apogee before gravity pulls it back down to start the whole cycle over.
I was trying to think of a good analogy for this, and initially I thought of a skateboarder in a half pipe, dropping in, going fastest at the bottom and slowing down at the top edge.
That works pretty well geometrically.
But given the military context we're talking about today, I think a better analogy is actually a sniper's breathing cycle.
Oh, I like where this is going. Walk me through it.
So when a sniper is setting up a shot, they don't fire while they are rapidly exhaling or inhaling. They fire at the natural respiratory pause.
Right, the pause at the end of the breath.
Exactly. They exhale, and there is that moment of utter stillness, that pause at the bottom of the breath where everything just slows down. They have maximum stability, and they take the shot. Then the rapid cycle of breathing begins again.
That's a great visual.
A satellite in a highly elliptical orbit acts exactly the same way. It races through its perigee, which is the rapid exhale, giving sensors almost no time to focus. But as it climbs to apogee, it enters that respiratory pause.
It slows way down.
Right, it slows down dramatically, almost appearing to just hover over a specific part of the Earth. And that stillness is when the critical work happens.
That is a brilliant analogy. And that respiratory pause at apogee has massive tactical implications.
Hope so.
Well, if you are a military planner, you absolutely exploit Kepler's second law. If you need to monitor a massive armored mobilization in a specific region, you don't want a satellite that just blurs past in 3 minutes.
No, you'd want constant eyes on it.
Exactly. So you intentionally design a highly elliptical orbit and place the apogee directly over your target area.
Putting the pause right where you need it.
Right. Your intelligence sensor whips around the opposite side of the planet, then climbs up over your target area, slows way down, and gives your analysts hours of uninterrupted, continuous observation before it speeds away again.
Wow.
You are literally using 17th century math to manipulate the hang time of a 21st century sensor.
That is incredible.
Kepler.
What about Kepler's third law?
Kepler's third law is the law of harmonics. It establishes a strict, unbending mathematical relationship between the physical size of the orbit and how long it takes the satellite to complete one full revolution, which we call the orbital period.
Okay.
The text states that the square of the orbital period is directly proportional to the cube of the satellite's average distance from the center of the Earth.
Okay, stop right there. Squares, cubes, proportionalities. Let's translate that right out of the physics textbook and into the Tactical Operations Center.
Fair enough.
What is the actual takeaway for the planner on the ground?
The takeaway is absolute certainty. Altitude completely dictates speed and timing.
Altitude is everything.
Everything. The time it takes to complete an orbit is strictly determined by how high the satellite is, regardless of its mass.
So a big satellite and a small one behave the same?
Exactly. If you have a 5-ton secure communications satellite and a 20-pound experimental weather sensor, and you put them in the exact same orbit at the exact same altitude, they will have the exact same orbital period.
They'll just fly side by side forever.
Yes. So mass doesn't matter, only distance.
Yeah.
And furthermore, because the gravitational pull weakens the further out you go, satellites at higher altitudes not only have a longer physical track to travel, but they are literally moving slower.
Altitude is the master dial that controls timing in the space domain.
That's a perfect way to summarize it.
So if we take all of this together, Newton's unyielding laws of momentum, inertia, and gravity, combined with Kepler's strict geometric laws of ellipses, varying speeds, and harmonics. What is the grand strategic implication for the joint force planner trying to utilize space?
The overarching strategic implication is absolute predictability.
Predictability.
Yes. Because these laws are absolute and unforgiving, a satellite's path is not a mystery. It is a highly predictable mathematical certainty.
Once it's up there, we know exactly where it's going.
Once a satellite achieves orbit, we know exactly where it is going to be tomorrow, next week, or next year, down to the millisecond.
But that predictability is a massive double-edged sword, isn't it?
It is the ultimate double-edged sword. On one hand, it is essential for our operations. We know exactly when a specific communication link will crest the horizon to support a special operations raid.
We know exactly when our imaging sensors will pass over an adversary's naval port.
Right. But the vulnerability is that our adversaries know the exact same physics. There is absolutely no stealth in orbital mechanics.
They can just run the math, too.
They know exactly where our assets are, and they know exactly when our unblinking eyes will be overhead. We cannot just randomly swerve a reconnaissance satellite to surprise an enemy.
Because, as we discussed with Newton's second law, doing that would require an impossible amount of fuel.
Exactly. The enemy knows our schedule because the universe publishes the schedule.
The universe publishes the schedule.
Yeah.
That is a really profound and slightly terrifying operational reality.
It definitely keeps planners awake at night.
So if the enemy knows the physics, and we know the physics, the next logical battlefield isn't how to stay in orbit, but how to mathematically map exactly where an asset is hiding in that infinite void.
Right, we have to transition from physics to geometry.
Exactly. If you want to utilize a friendly satellite, or if you want to target or evade an adversary satellite, you need an incredibly precise mathematical language to describe its past, present, and future position.
And to do that, space operators use a set of 6 distinct mathematical parameters called the classical orbital elements.
I'm going to be perfectly honest here. When I first started studying this doctrine, I pushed back hard on this concept.
Oh yeah? Why is that?
Well, if I am an air traffic controller, or an air defense artillery officer, and I want to find a friendly aircraft or track an enemy bomber, I really just need 3 numbers: latitude, longitude, and altitude.
Right, the standard coordinates.
I can pinpoint anything on Earth with those 3 numbers. So why does the space domain require this incredibly complex 6-part geometric address system just to find a satellite?
It is a totally valid frustration, but it really comes down to the environment itself. The reason latitude, longitude, and altitude work for an aircraft is that the aircraft is flying relative to the surface of the Earth.
Okay.
And crucially, the atmosphere is flying and rotates with the Earth. The grid is essentially fixed to the ground.
But satellites aren't in the atmosphere.
No, they're completely divorced from the Earth's surface. They are orbiting in an inertial, frictionless void. Meanwhile, the Earth is constantly spinning underneath that orbit.
Ah, right. The ground track is constantly shifting.
Exactly. If a satellite is passing over New York right now, by the time it completes one orbit 90 minutes later, New York has rotated hundreds of miles to the east.
So it's not going to pass over New York again.
No, the satellite will pass over a completely different part of the country. So before we can even begin to project a satellite's location down onto the geography below, to tell a commander when it will be over a specific battlefield, we have to lock down the orbit's absolute shape and its orientation in fixed, 3-dimensional inertial space.
The map isn't the Earth. The map is the universe.
Exactly. And navigating that requires 6 distinct elements.
Okay, let's build an orbit practically then. Let's say I am a planner, and I want to put a reconnaissance asset over a specific denied river valley in an adversary's territory.
Okay, let's do it.
I can't just say, put it at 500 miles up. I have to build it element by element. What is the very first thing I need?
First, you have to determine the overall size of the orbit. We do that with the first element, which is the semi-major axis.
The semi-major axis.
Right. We know orbits are ellipses. If you draw a straight line straight through the longest part of that ellipse, from the perigee on one side right through the Earth to the apogee on the far side, that entire line is the major axis.
So the semi-major axis is just half of that line.
Exactly. It represents the average radius of your orbit. And crucially, as we learned from Kepler's third law, this element dictates the mechanical energy and the orbital period of your satellite.
Okay, so I give you the semi-major axis. You know the size. Let's say it is 10,000 miles wide. But you still don't know if it is a perfect circle or a long, stretched-out oval, like the sniper analogy.
Right, which brings us to the second element, eccentricity.
Eccentricity.
Yes. Eccentricity measures the shape of the orbit. It dictates how stretched out or circular the ellipse is. It is measured as a numerical value strictly between 0 and 1.
So a 0 is what?
If the eccentricity is exactly 0, the foci merge and the orbit is a perfect mathematical circle. As the number grows closer to 1, say 0.7, the orbit becomes a more and more stretched out, flattened cigar shape.
And if it hits 1?
If the eccentricity hits 1 or higher, the orbit is broken. It becomes a parabola or hyperbola, and your satellite achieves escape velocity and flies off into deep space.
So with semi-major axis and eccentricity, you've now defined the exact size and the exact shape of your orbit.
You have the hula hoop built.
Okay, I have my hula hoop,
Yeah.
but I am just holding it in a void. We need to orient it around the Earth. I assume the first step is figuring out how tilted it is.
Yes, that is the third element, inclination. This is the tilt of the orbital plane relative to the Earth's equator.
How does that look visually?
Well, imagine the equator extending outward into space like a giant flat pane of glass. Your satellite's orbit is a second hula hoop intersecting that glass. The angle formed between those two planes is the inclination.
And this is incredibly tactical because the inclination dictates the maximum latitude the satellite will ever fly over, right?
Entirely. If you have an inclination of 0 degrees, your satellite is completely flat with the equator. It will never, ever see anything north or south of the equator.
But if you tilt it,
If you tilt it to an inclination of 45 degrees, it will fly up to 45 degrees north latitude, dip down to 45 degrees south latitude, and cover everything in between.
and a 90-degree tilt.
If you tilt it all the way to 90 degrees, it becomes a polar orbit, flying directly over the north and south poles, eventually scanning the entire spinning globe beneath it.
And the text mentions that if the inclination is between 0 and 90 degrees, it is moving in the general direction of the Earth's rotation, which is called a prograde orbit.
Correct.
But if you tilt it past 90 degrees, between 90 and 180, it is actually flying backward against the Earth's rotation. That is a retrograde orbit.
Exactly. So now we have the size, the shape, and the tilt. But here is the problem. You have a tilted hula hoop around the Earth. but you can spin that tilted hula hoop completely around the planet.
Right. Does it cross the equator over the Atlantic Ocean, or does it cross over the Pacific?
Exactly. We need to lock its rotational orientation in three-dimensional space.
Which brings us to the fourth element. And I'm going to stop you right here, because this element has the absolute most intimidating academic-sounding name in the entire doctrine.
I know exactly which one you mean.
The right ascension of the ascending node. It honestly just sounds like word salad. Why are we overcomplicating this? Why can't we just say the orbit crosses the equator over London?
I completely understand the frustration, but remember what we discussed earlier. London is moving.
Oh, right.
The Earth is rotating roughly 1,000 miles per hour at the equator. If you tie your orbit to a city, your reference point is constantly spinning away from you. We have to anchor the orbit to something that does not move.
So we have to anchor it to deep space.
Exactly. We anchor it to the stars.
Okay, so walk me through. What is the ascending node part of that crazy name?
Your orbital plane is tilted, intersecting the equator, right?
Yeah.
That means the satellite crosses the equator twice every single orbit, once while heading north and once while heading south.
Makes sense.
The exact point where the satellite crosses the equator, moving from the southern hemisphere into the northern hemisphere, is the ascending node. That is a specific single point in space.
Okay, I have the point. Now, what is the right ascension part?
Well, astronomers needed a fixed, unmoving anchor point in deep space to measure against. Centuries ago, they chose a specific directional alignment of stars known as the vernal equinox direction.
Just a completely fixed reference vector pointing out into the universe.
Exactly. The right ascension of the ascending node is simply the angle measured eastward along the equator from that fixed vernal equinox star point to your ascending node.
Okay, let me just make sure I really have this. We are literally measuring the position of our most highly classified, multi-billion-dollar military technology against a random constellation of stars deep in the universe, purely because the ground beneath our feet won't stay still.
That is exactly what we are doing. That angular measurement locks your tilted orbital plane in absolute fixed inertial space, completely independent of the spinning Earth below.
It essentially secures the hula hoop.
It secures the hula hoop.
All right, I get it now. It is brilliant, even if the name is terrible. So we have size, shape, tilt, and the absolute orientation in space. That is 4 elements. What are the last 2?
The last 2 elements place the physical satellite onto that track we just built. The 5th element is the argument of perigee.
Argument of perigee.
Right. We know the orbit is an ellipse, which means it has a low point, the perigee. But where exactly is that low point located within your tilted, locked orbital plane? Does it happen over the northern hemisphere or the southern?
So this locks the oval in place.
Yes. The argument of perigee is the angular measurement taken from the ascending node along the orbital path to the perigee. It locks the orientation of the ellipse within the orbital plane.
So it tells us where the sniper's respiratory pause, the apogee, will actually occur.
Exactly. And finally, the 6th element tells us where the actual piece of hardware is right now. It is called the true anomaly.
True anomaly.
Yes. Once you have the entire track perfectly laid out in three-dimensional space, the true anomaly is just the exact current location of the satellite on its path, measured as an angle from the perigee.
So you just put all 6 of those together. Semi-major axis, eccentricity, inclination, right ascension of the ascending node, argument of perigee, and true anomaly, and you have the cosmic address.
You have the complete cosmic address. You plug those 6 variables into an orbital propagator, and you can calculate exactly where that satellite was 10 years ago and exactly where it will be at 1400 hours tomorrow.
And for you, the listener, understanding this geometry is what really separates a novice from a space professional. It is what allows planners to know with absolute certainty when an adversary space station will be positioned overhead, or when our own communication link will be available.
It's the language of the domain.
Which leads us seamlessly into our third section today, real estate in the space domain.
The fun part.
Yeah. We have the physics, we have the geometric language to map it. Now we have to talk about the tactical applications of these specific orbital neighborhoods. Because military planners must choose the right terrain for the right mission.
Terrain is the perfect word for it. Just like a ground commander decides whether to place their forces in a dense urban environment or up on a high mountain ridge, a space planner has to choose an altitude and inclination that offer the specific capabilities required for the mission.
And we categorize this real estate into 4 primary orbits, right?
We do. The first, and definitely the most crowded neighborhood, is low Earth orbit.
Okay, low Earth orbit. That covers the region from just above the Earth's atmosphere up to an altitude of roughly 530 miles.
Correct.
And because it is so low, it feels the massive pull of Earth's gravity, meaning, per Kepler's laws, satellites here have to move incredibly fast.
Very fast. We are talking orbital periods of about 90 minutes. They circle the entire globe in just an hour and a half.
From a tactical standpoint, low Earth orbit is heavily utilized for intelligence, surveillance, and reconnaissance missions.
Oh, absolutely.
If you want to take a high-resolution photograph of an adversary's airfield, or if you want to intercept faint radio signals from a terrorist compound, you just need to be as close to the target as physically possible.
And low Earth orbit gives you that extreme proximity.
But there is a massive trade-off for being that close, isn't there? If you are a ground commander relying on a satellite in low Earth orbit, you are constantly fighting against its speed.
That is the crucial limitation. Because it is moving at 17,500 miles per hour to avoid falling back to Earth, a satellite in low Earth orbit is only visible from a specific point on the ground for a very brief window.
Like how brief?
If a unit in the field needs overhead support, that satellite will crest the horizon, scream across the sky, and completely disappear over the opposite horizon in roughly 10 to 15 minutes.
You get incredible detail, but you get almost no time. I picture kind of like looking through a soda straw. You get intense focus on a very tiny area, but the straw is constantly sweeping rapidly across the map. You can't just stare at one spot.
That's a great analogy.
What about the next neighborhood up? Medium Earth orbit.
Medium Earth orbit sits in the vast expanse between low Earth orbit and the really high altitude regimes. Specifically, we operate heavily around an altitude of 6,200 miles, with orbital periods ranging from roughly 6 to 12 hours.
And this is a very specific neighborhood, right?
It is the absolute ideal home for navigation systems. This is exactly where the United States military operates the Global Positioning System constellation.
Okay, let's unpack why. Why put the global positioning system all the way up at 6,200 miles? Why not put it in low Earth orbit where the signals would be so much stronger, or even higher up so you could see the whole Earth at once?
Because it is the ultimate Goldilocks zone. Let's just run the scenarios. If you put navigation satellites in low Earth orbit, they are so close to the Earth that each satellite can only see a tiny fraction of the globe at one time.
Right, the soda straw effect.
Exactly. To ensure a soldier on the ground or a guided munition in the air can always see the minimum of 4 satellites required to calculate a 3-dimensional position, you would literally need a constellation of hundreds, maybe thousands of satellites whipping around constantly.
It would be an unmanageable logistical nightmare.
Total nightmare.
And if you put them too high.
Well, if you put them way out at 22,000 miles, you only need a few satellites to see the whole Earth, but the distance is so vast that the signal degradation would be severe.
Oh, I see.
The transmitters would have to be massively powerful, and the receivers on the ground, like the handheld devices carried by infantry, would be way too large and consume way too much battery power.
So 6,200 miles is the sweet spot.
It is the perfect compromise. A moderate constellation of about 24 to 30 satellites can blanket the entire globe. Each satellite moves slowly enough that it stays in view of a user on the ground for several hours at a time, providing the continuous, reliable navigation and timing data that modern joint force operations completely depend on.
That makes perfect sense. The altitude is selected purely based on geometry and signal strength. So moving further out, we hit what might be the most strategically valuable real estate in space. Geosynchronous orbit.
A high ground.
Yeah. This sits at an incredibly specific altitude of roughly 22,300 miles. And based on Kepler's third law, at this exact distance, the orbital period of the satellite is exactly 1 day, 24 hours.
And this is where the physics create a profound operational advantage. Because the satellite takes exactly 24 hours to circle the Earth, its speed perfectly matches the rotational speed of the planet.
They move together.
Right. If you take that satellite and give it an inclination of exactly 0 degrees, meaning you place its orbit perfectly flat along the Earth's equator, it becomes what we call a geostationary orbit.
To an observer on the ground, that satellite doesn't rise or set at all. It appears to just freeze in the sky. It hovers over one single spot on the equator permanently.
Exactly. If low Earth orbit is a soda straw constantly moving, a geostationary orbit is a wide-angle security camera mounted high up on a wall.
I love that comparison.
It doesn't give you the finest, granular details of a specific truck on a road, but it provides a constant, unblinking watch over one entire hemisphere of the Earth.
And for the military, that unblinking presence is totally non-negotiable for certain missions, right? Like strategic communications and missile warning.
It is absolutely essential. For satellite communications, a geostationary orbit means a forward operating base can point their satellite dish at one specific coordinate in the sky, lock it in place, and literally never have to move it.
The link is just always there, 24/7.
Always. It is also the primary orbit for our strategic missile warning sensors. Those infrared sensors stare constantly at the Earth's surface, never blinking, just waiting to detect the immense heat bloom of an adversary's intercontinental ballistic missile launch.
You definitely cannot afford to have a gap in coverage for that mission.
No, absolutely not.
But there is a glaring geographic blind spot with geosynchronous orbits. Because they are parked directly over the equator, they have a really terrible viewing angle of the extreme northern and southern latitudes.
The curvature of the Earth gets in the way.
Right. The Earth literally curves away from their line of sight. If you have sources operating near the North Pole or submarines surfacing in the Arctic, that wide-angle equatorial security camera cannot see them or communicate with them clearly.
That is a major tactical limitation. And it brings us to the final orbital regime we need to discuss, which we actually touched on earlier. Highly elliptical orbits.
The sniper breath pause.
Yes. To solve the polar coverage problem, aerospace engineers utilize extreme eccentricity. The most famous example is the Molniya orbit, which was actually pioneered by the Soviet Union because so much of their landmass is in the extreme northern latitudes.
So they use that sniper's respiratory pause. They set the perigee very low in the southern hemisphere and the apogee extremely high over the northern hemisphere.
Precisely. They use Kepler's second law as a literal weapon. The satellite whips around the South Pole in less than an hour, minimizing its time in the useless hemisphere.
Wow!
But as it climbs up toward its apogee over the northern hemisphere, it loses speed and essentially hangs or lingers over the high northern latitudes for 8 to 12 hours at a time. It completely bypasses the equatorial blind spots.
That is brilliant.
By using a constellation of just a few satellites in these highly elliptical orbits, spaced out perfectly, as one satellite speeds away, the next one arrives at apogee, guaranteeing continuous communication and missile warning coverage for the polar regions.
It is just an incredibly elegant solution using pure math. So we have our physics, our geometric address system, and our prime real estate. But the reality is, space is not a perfectly clean, pristine mathematical void.
Not even close.
If we assume the universe acts exactly like the textbook says, our satellites will eventually drift, fail, or just fall out of the sky.
Which brings us to our fourth and final section for today. The bumpy ride.
The real world.
Right. We have to talk about orbital perturbations and launch considerations.
This is exactly where theory collides with reality. Everything we have discussed so far assumes a perfect, uniform universe. It assumes the Earth is a perfect sphere, it assumes there is no atmosphere, and it assumes no other planets exist.
Which is just not true.
But to operate effectively across the competition continuum, planners must account for the messy reality of the physical universe that constantly disrupts these perfect mathematical orbits. These physical disruptions are called orbital perturbations.
Let's start with the Earth itself, because the Earth is definitely not a perfect sphere. It is not. Because the Earth is spinning on its axis, centrifugal force causes the mass at the equator to bulge outward.
Like a spinning water balloon.
Exactly like that. The planet is slightly flattened at the poles, making it somewhat oblate or pear-shaped. This uneven distribution of mass is called Earth's oblateness, or the J2 perturbation.
I try to picture this spinning water balloon bulging out. But how does that physical bulge affect a satellite hundreds of miles away in the vacuum of space? Does it mean the satellite's ground track is constantly wiggling? Do we have to burn precious fuel just to fight the shape of our own planet to stay on course?
It actually has a massive effect. The extra mass at the equatorial bulge exerts a slightly different gravitational pull on the satellite than a perfect sphere would.
Oh, because there's literally more rock there pulling on it.
Exactly. As a satellite crosses the equator in a tilted orbit, that extra mass tugs on the orbit, causing the entire orbital plane to slowly drift or rotate around the Earth over time.
Just slowly turning the hula hoop.
Yes. This rotational drift is called precession. And you are right. If you want your orbital plane to remain perfectly fixed in space, pointing at the exact same star forever, you would have to constantly burn fuel to fight that gravitational tug.
Which we established is very bad.
But brilliant space strategists realized decades ago that you don't fight it. You actually harness this ablateness to your advantage.
Tell me how. How do we turn a perturbation into a feature?
By carefully calculating a specific altitude and a specific inclination, usually a retrograde orbit that is nearly polar, around 98 degrees, aerospace engineers can ensure that the rate of that gravitational drift caused by the bulge perfectly matches the rate at which the Earth travels around the Sun.
So the drift matches the year.
Right. The equatorial bulge literally pushes the orbital plane forward at roughly 1 degree per day, exactly mirroring the Earth's annual journey.
Resulting in a sun-synchronous orbit. I've read about these.
Yes. Without using a single drop of fuel to maintain it, the satellite's orbital plane stays locked at a specific constant angle relative to the Sun all year long.
Which means the satellite passes over a target on the ground at the exact same local solar time every single day. If it crosses over an adversary's missile silo at 10 a.m. on a Monday, it will cross over that same silo at exactly 10:00 a.m. on Tuesday.
And think about why that matters to an intelligence analyst. The shadows cast by the Sun will be identical day after day.
Oh, wow. The shadows.
Yes. If an analyst is looking at a reconnaissance photograph from yesterday and they compare it to a photograph taken today, the lighting is exactly the same. If a shadow has changed or if a shadow has appeared where there wasn't one before, they know with absolute certainty that something on the ground has physically changed.
That is genius.
They can spot a new tank, a relocated radar array, or a decoy with incredible accuracy. It is a massive intelligence advantage, powered entirely by the fact that the Earth is slightly pear-shaped.
That is an amazing use of a physical flaw. What about the other disruptions? We mentioned atmospheric drag earlier when we talked about low Earth orbit.
Atmospheric drag is relentless. Even at altitudes of several hundred miles, an area we generally consider to be a vacuum, there are still trace particles of atmospheric gas.
It's not totally empty.
Not totally. When a satellite moving at 5 miles per second smashes into these microscopic particles, it creates friction, or drag. That friction constantly steals kinetic energy from the satellite. Over time, this loss of energy slows the satellite down.
And as Newton and Kepler taught us, if you lose velocity, you lose altitude. The perigee begins to drop.
Exactly. Left unchecked, the satellite's orbit will slowly decay until it enters the thicker parts of the atmosphere and burns up completely.
Like the space station, right?
Yes. The International Space Station, for example, is massive and flies in low Earth orbit. It experiences significant drag. To counter this, operators must periodically fire thrusters to boost the station back up into its nominal orbit.
And again, firing thrusters requires fuel. Once the satellite runs out of fuel to fight drag, its operational life is on a strict countdown. Are there any other major perturbations we need to track?
We also have to account for third-body effects. Remember Newton's law of universal gravitation. Everything attracts everything.
Right.
When a satellite is in a very high orbit, like a geosynchronous orbit 22,000 miles out, the gravitational pull of the Earth is weaker, which means the gravitational pull of the Sun and the moons start to become mathematically significant.
They start tugging on it, too.
Over time, the gravity of the Sun and moons subtly yank the satellites away from the Earth's equatorial plane, slowly changing their inclination. If you want your communication satellite to remain perfectly geostationary, you have to constantly perform small fuel burns to maintain your exact position against the pull of the solar system.
So space operations are an endless, fuel-consuming battle against the environment. And that battle actually starts the literal second a rocket leaves the launch pad. Our doctrine text outlines the physics of launch considerations. It explains why the United States launches from specific locations like Cape Canaveral in Florida and why we almost always launch our rockets toward the east.
It all comes down to energy conservation. As we have discussed, achieving orbital velocity requires an immense, violent amount of energy.
Right.
You are trying to push thousands of pounds of hardware to 17,500 miles per hour. The Earth rotates from west to east. If you stand on the equator, the surface of the Earth beneath your feet is already moving eastward at roughly 1,000 miles per hour.
So if you launch your rocket toward the east, you get to give that rotational speed. The Earth literally gives the rocket a 1,000 mile per hour head start.
It is a massive free ride. It saves huge amounts of fuel. If you launched to the west, you would have to burn fuel just to cancel out the Earth's rotation before you even started building up orbital speed. It would be incredibly inefficient.
Which means by launching east, you can pack a larger payload, or you can pack more station-keeping fuel for the satellite once it gets to orbit, extending its lifespan.
Exactly. And the physics also dictate where we launch from. The closer your launch site is to the equator, the faster the Earth is spinning at that latitude and the more rotational speed you capture.
Oh, that makes sense.
That is exactly why the United States launches its heavy geostationary communication satellites from Florida or Texas, rather than from high-latitude bases in Alaska. You are trying to wring every possible ounce of physical efficiency out of the geometric rotation of the planet.
Okay, let's pull all of this together. We have covered a massive amount of ground today. We have broken down the fundamental, unforgiving physics of Newton and Kepler. We have built the 6-part orbital geometry system that maps the sky.
We cover the neighborhoods, too.
Yes, we explored the different orbital neighborhoods that house our specific military capabilities, and we have unpacked the chaotic perturbations that operators battle every single day. As we close out this deep dive, let's synthesize what this all means for you, the listener, as a future Joint Force planner or commander.
The ultimate synthesis is this. To integrate space operations into any tactical or regional scenario, you cannot simply view the space domain as a magic, high-ground utility where things always work on demand.
It is not an ATM where you just withdraw intelligence or communications whenever you want.
No, it is a harsh physical environment governed by strict, unyielding laws.
If you are going to leverage space, you must intimately understand the physics that dictate when a vital communication link will actually be available to your troops. You have to know the geometry to understand how long an intelligence sensor will linger over your target based on its perigee and apogee.
And you have to understand the brutal reality of momentum and fuel costs to know why a navigation satellite cannot simply change course on a whim to support a shifting ground maneuver.
The space domain is foundational to all other domains. Air, land, and sea operations rely on it completely. But space operates on a rigid mathematical clockwork rhythm.
Military planners must adapt their terrestrial operations to the rhythm of space, not the other way around.
And that leads to a final, slightly provocative thought for you to ponder as you move forward in your studies. Consider the paradox of what we have discussed today.
It is quite a paradox.
The most advanced, highly classified, multi-billion-dollar military technology of the 21st century. The systems that enable global strike capabilities, coordinate instant worldwide communication, and guide precision munitions, they are entirely at the mercy of celestial mechanics, discovered by men looking at ledgers and staring through rudimentary glass tubes in the early 1600s.
It really puts it all into perspective.
We may own the cutting-edge technology, and we may dominate the domain, but the universe entirely dictates the rules of engagement.